Austin, why are you over there?
So, let's practice one more time. This is your homework. Let's practice one more time. This is 11.3, number 5. You're welcome. Finally, this class I definitely can show some of your homeworks because we're going to practice a lot. 11.3, number 5. Find the partial derivatives of this. And by accident, I have Carla's account open, so that's actually your problem. Yeah, by accident. So partial derivatives, let's remind you what it is. Post your questions in the forum. We are happy to help you there. Don't stuck by yourself. Don't feel lonely that you are behind or you feel I'm not good enough, the imposter syndrome. Don't do that. Post it in the forum. We have amazing community in the forum, so just do that. So partial derivatives means what? F, sometimes we call z also, as you can see on the right hand side, it says, oh, let's call f z, which, oh, no, that's not what I want to say. Ignore that. F depends on, because we do it sometimes, but not in this case. F depends on x, y, z, and we are asked to find derivative with respect to first variable, second variable, and third variable, x, y, and z. At the particular point, so before plugging in the point, you first find partial derivative of f with respect to x in general. That means your brain now should tell you, is this weird that I'm assuming all of us talk to our own brains? I don't know. So your brain tells you, okay, remember dudes, x is a variable, y, z, and everything else are constant. Now you're imagining this and you're taking derivative of z arctangent y over x. Is this product rule then? No, because z is a constant. If it's easier for you, imagine z is 10, y is 10, or 100, or whatever you want, 1. Now you only see that x is a variable. Okay, so then z survives because it's multiplied and it's a constant. What is derivative of arctangent?
1 divided by the square root of something. 1 square.
So 1 over square root 1 plus. Oh, is it a square root there or not?
No, I think it's 1 squared plus x squared.
So arcsine, arccosine have square roots. Arctangent is the only one with plus and no square roots. And it says 1 plus input squared. And that's why in calculus 1 I teach it this way. Input squared, whatever your input is. My input is this, whatever is inside of the parentheses. So I'm gonna copy it and square it. That's the derivative of the function outside. Function outside is arctangent. Times chain rule steps in. Chain rule says, wait, there's something inside. This is a simple chain rule. In a second, I'll show you complicated chain rule. Chain rule says there's a function inside of arctangent called y over x. You have to differentiate that, but your mind is keep bugging you. Oh, remember, x is a variable, y is a constant. So what is derivative of y over x? Over x squared. Agree, disagree, comments? Do you know how I did it? So I wrote it as y times x to the minus 1 prime. Y is a constant, so it survives. Survives means it's not 0 because it's multiplied. And then I have minus x to the minus 2. Derivative of x. Agree on this? You can simplify or not. You can just plug right away your numbers. 2 minus 4. So you found, let's find all the 3 derivatives. Sometimes there's a very nice notation I taught you in previous classes, if you took it with me. A bar, and then we plug 2 minus 4. That's a very nice shortcut notation because you don't have to rewrite everything again. And then, since this is new for you, maybe take a pencil and write down, this is x, this is y, this is z. In time, you get used to it. Phi, psi, theta, or theta, phi, and we also do usually sigma. Yes, sigma, delta, and so on. So sometimes you get used to it. I, j, k. Now I'm plugging in. So the bar means at. Derivative at. 2 minus 4. And you carefully plug it in, or you can simplify if you want to. I don't want. Z is minus 4. 1 over 1 plus y over x, 2 over 2 squared, times, I could put it in the numerator, minus y, which is 2, x is 2 squared, and I see it's supposed to be minus 2/5, minus 2 over 5. Can you do this? This is a very good exam question, to be honest. How about that? Not too bad, or it is bad. I don't know. It's like you need to be awake when you do the second exam. In general, it's very nice if you're not sleepy during the tests. But I would say the partial derivatives are the one that requires awakeness. You know, you should be awake to make sure you don't mess up these little steps. Who is y? Who is z? Okay, let's do b. B is partial derivative. That's why it's curly. With respect to y. I'm looking back to the same function, and now my brain has to switch. I'm asking my brain, please forget that x used to be variable. Don't push me this idea anymore. X now is a constant. Z is a constant. Y is a variable. So it's still not a product rule. Z is still a constant. Arctangent still gives you 1 over 1 plus input squared. And your input should be copied. Remember chain rule. Times. And now you have derivative of y over x, where y is the variable. So what is derivative of that?
1 over x.
1 over x. Agree, disagree? Y over x, I'll make a note here for b. Y over x is y times 1 over x. 1 over x is a constant. So it's just 1 over x. Make sense? Because y is like 10. Maybe if you see that, your brain will like it more. A bar, and now we're plugging the same point. 2 minus 4. And then you repeat the process, so I don't have to write it down the whole thing. 2/5. Does that make sense? What do you think? X, Y, and Z. X, Y, and Z. And the last one will be the most interesting one. C. Yeah.
How did you get 2 over 5 for the first one?
2 minus 2 over 5. I don't know. I just copied it. So let's see. Oh, yes. Carlos has different numbers. Okay, who got the answer for the first question?
I got 2.
You just got 2? Okay, then I'll have to calculate it. I really do not want to. Minus 4 times 1 over 2 times, what is that? Minus 1/2. So, oh yeah, it looks like 1. Yeah, okay, this is 1. Sorry about that. Yeah, Carlos has different numbers. I just realized that. Then this one,
I can't believe it. You're all our fault.
question mark. Yes, your homework, do yourself.
I can do it.
Yeah.
I actually blame Carlos.
-2.
Did you? Oh, calculate?
I don't even have a -4. That's the thing.
I think it's -2.
Okay,
My problem.
It's -1. Yeah. Oh, it's -1.
1 or 2?
No.
Let's just keep it for exercise. You know how professors say when they just don't like moving on, they're like, this is your exercise. And nobody ever do that at home. The last one is the most interesting, partial derivative with respect to z. Why it's the most interesting? Let's see. Your brain looks back to the function. I'm zooming in, and your brain is like, I think y is a variable. You're like, no. None of this is a variable anymore. Z is the only variable. This is some kind of constant, like 10 over 5 or whatever you want. So what is the derivative of this?
Just arctangent.
Just arctan. There's not even differentiation of arctan anymore. Do you all see that? No. So the last one is the best one. Let me write down and I will explain.
That's the easiest.
Arctan of y over x. Done. Why? Because if I'm taking derivative with respect to z, only z is the variable arctan of 10 over 7. So whatever you want, constants. What is z multiplied by arctan of constant? It's just derivative of that is just arctan of the constant. Make sense? That's like the most easy one. And we never did product rule, as you can see. A bar plugging in 2 minus 4. So again, a bar means at. That's a very popular notation. And becomes arc10 of y over x 2 over 2. That is just arc10 of 1. Arc10 of 1. What tangent of what angle gives you 1? Pi fourths. Good job. That one was actually the easiest one to calculate. This is an amazing problem for the test. Yes.
Can you explain again why it's arctan?
Yes. So let's see. For C, I will color code it. For C, I'm taking derivative df with respect to z. That means z is the only variable. Arc10 in black is y over x. This is a constant. What is derivative of the variable times constant? Just that variable, derivative of that variable. Derivative of z is 1. Constant survives because it was multiplied. Arctan of y over x. Does it make sense?
So it's like treating arctan of y over x like
Complete constant.
like saying it's like 2. So then just
It's like, yeah, let's do like 100, yeah? So it's z times 100. What is derivative of z times 100? 1 times 100. So that's how confusing it is for your brain at first, but then you kind of start enjoying it. Somehow I really enjoyed partial derivatives because of this. It's logical, and it also makes you think outside of the box. Again, the example with the cards. Can the hearts in the cards be black? If you see hearts and they're black, it's confusing you at first, but it is possible. So you have to think outside of the box that y over x is not a quotient rule anymore. Arctan of y over x is not even a function anymore. It's a constant. How cool is that? So you have to train your brain to see outside of the box, and it's very healthy. That's very good for your brain. Chain rule. Should I go back? Yeah, just a second. So chain rule. We kind of did chain rule right now and in implicit differentiation, but I wanted to introduce you to upper dimensions of chain rule inside of the upper dimensions of chain rule because it's awesome. And this, whatever we just did, is perfect for the test, but there is something cooler than that. And I wanted to show you. I did mention it in calculus 1. Soon in calculus 3 you will learn what if z or x or y also depends on some functions. For example, t. Then it's going to be chain rule inside of the chain rule inside of the chain rule. T is inside of x, x inside of f. What if z depends on two functions, t and g, that's gravitational forces. Now we have three functions, each depends on two functions, and each depends on one function, and that becomes 7-dimensional chain rule. And it's pretty cool to understand how to work with that because the idea is still the same. This is not new. This is review. The old chain rule we learned, I'm still fighting with chain rule in my other class right now, and they think it's very hard, is... Yeah, they're right. Chain rule is the hardest part. We're going to do implicit differentiation with them today in calculus 1. I also like this topic, yeah. So we taught it this way. I teach it this way. This function inside is u. So like a Russian doll, you see a function outside that is f. You first differentiate f. You copy your u because you have no rights to see it yet. Times chain rule shows up and says, look inside. There's a g inside, differentiate the function inside. This is how it taught you in calculus 1. What if z depends on two functions, just like right now, but each function, each x and y, depends on the third variable? Let's try that. So what I'm talking about is, so those are upper dimensions. Then z becomes a function f at x, but x is the function g that depends on time t, comma, y, but y is the function h that depends on time t, like so. So I plugged in. So each input is a function itself. So remember, function is like a machine. You have input comes in, it does something and gives you output. What if my machine swallows functions and then gives you out a function? So that's a pretty cool idea. Then chain rule looks like so. It's a little bit more interesting now. Compare with the previous result. So you will have both partial derivatives and not partial derivatives. See the difference, the curled d, delta, and just d. To differentiate this function z I just mentioned, here it is. To differentiate, I'll even put it in the box. This function d, you still repeat the same process. That is why my brain actually enjoys this process, because I see it's very logical. You still do the same idea. You differentiate the function outside. So look at what I'm asked to do here. I'm asked to differentiate to the very last variable, to the smallest Russian doll, t. So I want to dig into the very last inside t. To do that, I need to do it in order. I'm first differentiating z, which is this one, with respect to x. And I'm using partial derivative notation because x also depends on something. So it's only, no, because z depends on something, so it's partial derivative. Chain rule happens here, chain rule. And chain rule says, oh, but x also is a function. Differentiate that. Now it's not partial derivative anymore because x only depends on t, only one variable, for now. So now we're differentiating with respect to t. Plus, we did not finish. Now I'm going to differentiate with respect to y. With respect to y. Same idea, times. Chain rule happens again and says, oh, y is also a function. It's actually h of t. And now it's not partial derivative anymore. It used to be partial here, but it's finite over here. That is a pretty straightforward idea. When you start doing it, you actually understand it makes sense. It just looks a little bit scary. And some people show it as a diagram. The diagram looks like so. My function has x and y. X is a function of t, and y is, you don't have to copy this to be honest, it's just a diagram. Y is a function of t as well. If I want to reach the final destination with respect to t, I need to do both partial derivatives. First partial derivative with respect to x, that's why it's curled, and then, so you see, with z with respect to x, and then x with respect to t. Then plus derivative of z, partial derivative with respect to y, I dig into y, y unlocks the function of t, and I'm differentiating t. And that's how I get two products, dz over dx times dx over dt, plus dz over dy over dy over dt. As you can see, this match. So it's unlocking Russian dolls, basically. Let's do the example. You can check this website I just opened. So here's the example. Let's do it. The function z, example. The function z is a function f of x and y, and it's given as 4x squared plus 3y squared. Looks very simple. What's the problem here? However, x is x of t, and it's defined as sine function. I will put it in green. And then y is a cosine function of t. Thus, Thus, a note. You can also differentiate it this way. Z is actually a function of x, which is sine t, and y, which is cosine t. And it's going to be 4 sine t squared plus 3 cosine t squared. So technically speaking, you could just plug them in. Sine is in green, cosine is in blue. That is my y, that is my x. And technically speaking now, you can do it the way we just did, partial derivatives. We can just find derivative with respect to x or with respect to y and so on. The thing is, people don't do it. They don't actually plug those functions in. They do differentiate with the formula I just used. And I will do it first, and then I will explain you why later. So let's find all the pieces. That's why it's a note. All the pieces. We want to perform this formula below. We want to differentiate z with respect to x first. So let's find that. It's a partial derivative because z has 2 variables. That's why you need to choose which part you're using. When you have to choose, that's partial derivative. Now you just do whatever we did in the example before. Your brain should say, okay, x is a variable. So it's going to be 8x, and then 3y squared is a constant. So it's plus 0. Make sense? Plus 0. If you want, I can write down. Y is a constant in this case. That is a partial derivative. In black color, I finished this part. Times derivative of x with respect to t. Okay, this is not a partial derivative. That is a finite derivative. Why? Because x only depends on one variable. There is no choice here. X is actually in green. So let me put it in green. Here it is. In green. Derivative of sine. There's no partial derivatives here. Derivative of sine, I will write down for you once, is cosine. Cosine t. We are done with this first part. Plus, I'll put a bar in the rainbow, like so. Now, let's do black. Partial derivative of z with respect to y. It's partial because I have a choice. And I'm choosing now differentiate with respect to y. I'm looking again at this function in the black box. And now my brain tells me, okay, 4x squared is the constant now. Put 0. 3y squared gives me 6y because y is a variable. Agree?
Yeah.
Hope so. Finally, in the blue color is the not partial derivative of y with respect to t. There is no choice because y only depends on t. It's cosine. Derivative of cosine is minus sine t. And we are ready to complete this partial derivative with respect to t. So you see, all of this struggle is because I'm digging into the smallest Russian doll. The smallest Russian doll I have. And I have to multiply now. In black color, dz over dt is 8x. In green color, dx over dt is cosine t plus dz over dy is 6y times blue color derivative of y with respect to t is minus sine t, and that is the answer. How about that? You can simplify if you want, but
leave it up for a little bit, please.
yeah. Let it sink in a little bit, and then I also want to explain it this way. The way this.
Would you at any point need to plug in the x and the y?
Oh yeah. But I'm doing it right now. Thank you. I just wanna. He's right. Isn't it weird? We have answer with 3 different variables. At some point, we have to go into one unique variable. Usually the one that we ask, t. So we have to go back and remember what was your y, plug in with the t, x, plug in with the t, and we have it over there. You're right. I just want to make a pause right now. And yeah, there were questions, and then I will explain something else here.
So, does this answer, is it like the slope when you plug in all the values? What does it represent?
Yeah, it's a derivative. She's right. It's a slope, and this is the next chapter, slope of the tension. Okay, good job. So, you know how I see it, to be honest? At the very first clause, 4x squared. I know that I need to differentiate all of this. And at some point, each variable will be a variable and each variable will be constant at different steps of its life. 4x squared gives me 8x. Here it is. Times derivative of the function inside. X appears to be a function. I'm going to the list and I'm finding there's a list, say I have 15 functions. In this list, you find that x is sine. So times derivative of sine, cosine, plus 3y squared is also a variable at some point. It's going to give me 6y. Here it is. Times, since y is also a function, there's a whole list of functions. Maybe the whole English alphabet, right? X, Y, Z, T, M, T, N, T, O, and whatever you want, Z. I find in the list, y is a cosine, derivative of cosine is minus sine. So this is how I see it, to be honest. They teach you step by step, which is fine. I also was taught like this. But at some point I just realized, no, it's still changing. It's still derivative of outside times derivative of inside. But then plus derivative of outside times derivative of inside plus, and so on and so on. Moreover, it might keep going if t is also a function, then it's times derivative of the t and so on. So, smart comment was that way too many variables in the answer. That is not good. Readers usually don't like it. So let's switch back. Everything should be in terms of one variable. So let's remember that in green, x was cosine, and then in blue, y was sine t. So I just go back and 8 times cosine t, checking, everything is fine? Yes. What?
Wasn't X?
Different one? Yeah, that's what I was trying to check. It is different. So sad. Switch. Sine t. So it's going to be sine t plugged in. But there was also cosine t over here, standing, plus 6y. Y is in blue, y is cosine. Cosine t, so it's going to be cosine t in blue, but there was also minus sine t standing outside. Going. Sine t standing outside. And then if you simplify this, guess what we get? If you multiply everything out, it's going to be 8 sine t cosine t minus 6 sine t cosine t, which is a 2 of sine t cosine t. So it actually simplified in a very nice looking function. Everything in terms of t, as you can see. So this is a slope of the function. Well, it's derivative of the function with respect to the deepest last moment t, deepest variable you can have. Pretty cool? Yeah.
What was the notation for this? I know for
Yeah.
the partial derivative of z to the
Just that, the partial derivative with respect to t, and then if you want to know what it means, you have to go back and find what is z. So I'm going back, I don't know, right? I'm looking what z is. Oh, z is 4x squared plus 3y squared. But wait a second, they asked me to find derivative with respect to t. Where is t? And then I'm digging inside into my list of functions, and appear to be that x is a function and y is a function. Very interesting that it's not always like this. Maybe there's like t cubed at the end, right? So some of them might be functions, some of them might not be. Some of them are just variables. And that's how you read those scientific articles. What is the function and what is not a function? Not this. Okay. How about it gets crazier? I don't know how to call this. Let's call it, there's no particular name for this. Let me see if there is. Not really.
Very scary.
Harder, yeah.
Very scary.
Harder. Right? But then like smiling face to be encouraging. So z is still z is a function of two variables, x and y. How can it get worse, right? X is a function of two variables, u and v. Or maybe three variables, u, v, t. Or maybe five variables, u, t, v, m, g. Y is a function, let's call it h, g and h. That even doesn't matter. You see, I never actually used the name of those functions, to be honest. Also is a function of two variables. So if I want to rewrite this, like I did last time, if I want to be specific, that makes z to be a function of x, which is actually g of u and v, comma, then y is a function h with which is a function of u and v, comma. So if I want to see, now you see it's a every time you have several variables, that indicates number of dimensions. This is a two-dimensional function, which is flat. That is pretty simple. X and y, u and v, height and length, run and rise. But that function is only a first variable of another function. So f is also two-dimensional. But f is a function of z. So z is actually with f together is three-dimensional. So it's two dimensions inscribed in three dimensions. That's how you should see it. How cool is that? Then channel becomes like so. The thing is, I can ask to dig into different locations of the diagram. In the previous diagram, I wanted to mention this. I could actually stop over here, to be honest. It's not always we need to dig into the very last moment t. Sometimes I just want to find derivative with respect to x and be done with this. Then it's exactly what we did right at the beginning of the class. We just like, okay, x, the last one we like the most. Z was the variable, derivative was just arctan of y over x. Even though y and x may be variables, we might not even need to dig deeper into the Russian doll nests of functions instead of the functions. Sometimes we're asked only to stop here. So in this scenario, here it is, z depends on two variables, u and v as the finite destination. U is the finite destination like used to be t. And v is the final destination, like used to be t. Now they're just two different final destinations. And now each of them gives you partial derivatives. You see, all of these derivatives are now partial derivatives. dz over dx is derivative of the function outside. X can be, you open the Russian doll. Now x is a function. Differentiate x with respect to u, but it's partial because x has two variables, u and v. Plus, go back to the z, differentiate z with respect to, let's choose pink color, y, that unlocks another Russian doll. Y is partial derivative with respect to u because it has two variables. And that's how you dig into u. That's how you get into the u, the final destination. So that is my u, last destination of the Russian doll set. But what if I want to get into the v? Then I repeat the whole process, but keeping in mind that the very last step will be different. The first step is the same, but then x is differentiated with respect to v. The first step is the same, but y differentiated with respect to v. So the first two steps are the same, they just unlock the outside function. But inside function has a choice. Where do you want to go now? That is why it looks like this kind of tree. Those are called trees. I'm first differentiating the function with respect to one of these variables. If x, then I go up over here. If y, then I go down over here. Then from here, it used to be no choice, it used to be just t. But now, x also has two choices. If I want to go to u, I will go here. If I want to go to v, I will go here. And y has two choices. If I want to go to u, if I want to go to v. That's why it gets more complicated. And that's why the formulas are like so. And if we're not going to do this example, you can check it at home. I would recommend you to practice it at home because it's fun. I actually do think it's fun. And I gave you solutions. This link gives you to a solution of this problem. So this is homework to practice. Try it. Try it to practice, right? And is it S somewhere? No? Okay. Practice at home. So again, what is the confusion here? You don't have to write this down. 3x squared minus 2xy plus y squared, but x, look at that, how cool is that? X is a function 3u plus 2v, how cool is that? And then y is a function 4u minus v, how cool is that? Why did you do that? So that is interesting. Are you? No? Okay. Last try. Yes. So practice this at home. That's very interesting. Generalized chain rule looks like so. Very simple. Look at that. Infinitely many combinations. Infinitely many, and it is true. I think I mentioned in my calculus 1 class. My colleague in the PhD program, she was coding only behavior of one tissue cell. Mathematical biology, we model by behavior, cancer, tissues, neuroscience, and stuff like that. So she wanted to model how one tissue cell interacts with other tissue cells. How does your cells grow? How do they die? How do they substitute each other, and so on. It took her 75 equations with 75 dimensions to model only one cell behavior inside and talking with other cells. So she had 75 equations with 75 variables. And her PhD was about reducing the dimensions, and she was able to do it. She reduced it, I think, into 17, only 17 dimensions. That was a whole PhD program. So every time you add a variable, it makes it more detailed, but it makes it more complicated because now speed of each change, how the center is growing, how it gets the food, how it communicates with another cell. Each of these changes are partial derivatives, and that involves chain rule. So this is your infinite chain rule. And yeah, it's pretty cool. Last thing I want to show you is applications. Before we move on to the next topic, which I don't really have time for, but okay. Cool applications. Laplace equation is one of the most important ones. Looks like this. Look at that. Second derivative gives you 0. Laplace equations are amazing. You will see them quite a lot. Heat equations, people who will do physics, you will see heat equations, how fast the metal cools down, right? So heat equations have lots of applications. Those are partial derivatives. That's the cooling process. So you will see this. The heat equations look like so. The heat equation looks like so. Partial derivative, and soon you will learn this notation. We're gonna do it in this class soon. So this is called Laplace operator. Now, this, I think it's the same thing. Yeah. This guy is famous. Wave equations. Wave equations are pretty interesting. The wave, sound wave, water waves, they look pretty cool as well. Each equation is so famous that they have their own Wikipedia page and they taught around the world. So that is also pretty cool. Wave equations look like that. And let's see. Finally, what does this look like? So guess. I wanted you to guess. What do you think this equation will represent?
A stapler.
What?
A stapler?
I don't know, like when someone stabs you.
Yes, it's very interesting.
It does look like stabbing.
Anyone?
Looks like a table.
Dropping a marble?
Space? No?
What's the space time?
No?
Gravity?
Black hole.
Oh.
Black hole has its own equations. Navier-Stokes equations actually do, I gave you the link to check out, they do model black holes. It's called Einstein field equations, and they are responsible for modeling black holes. So they also have partial derivatives, gravitational forces, and so on. So let's see if I have animation here. No, that's the same thing. And for the last 5 minutes, we're not done. For the last 5 minutes, we're gonna cover the whole chapter. Just a second. No, I'm just gonna start it. It's fine. Tangent planes and linear approximation, it comes very naturally after partial derivatives because, as you can see, tangent plane will be created from derivatives. Tangent plane has two different tangents, and you can see it on the picture. Why it's going to be so important? Here are the very nice animations I found for you about tangent planes. Tangent plane will not only, so tangent, equation of the tangent line, which we just tested here, shows you how the functions increasing in 3D. Why plane is so important? Plane will give you approximation. Do you remember, I wanted to show you, in calculus 1, we keep talking all the time, you guys should stop. In calculus 1, I did teach you this. Where is my Desmos? Let's see. I did teach you this idea. Do you remember? Let me see. Where is my Desmos? Here. Sine and line y equals x. In calculus 1, I taught you that if you zoom in, you zoom in, you zoom in, at some point, you cannot see the difference between sine x and y equals x. So why to bother working with sine if you can just work with y equals x? That is a very simple way. Y equals x, 5 gives you 5. 2 gives you 2 versus sine of 5. I don't know what is that. So linear approximation was a big deal in calculus 1, and now we're going to do that using planes. The same idea with planes. And that is the coolest idea, I think, in 3D. Think about that. If there's a 3D shape called surface, why not to find a plane, that touches the surface at one point, zoom in, and if it's close to the plane, instead of working with a complicated surface, work with something simple, which is a flat plane. So we're going to do this, and then we need to teach you how to create those equations. Pretty cool. Okay, have a good day, and see you Friday. Don't get sick.